Welcome to the tutorial on Mentor, Siemens, Catapult HLS and ESP, an open source platform for agile system-on-chip development. In the tutorial, I will illustrate how to design an accelerator with the C++ flow of Catapult HLS. Please note that Catapult HLS supports both C++ and System C as design specification languages. In the tutorial, I will describe some of the aspects of a C++ synthesis flow. With the ESP team, we are working on the Catapult HLS System C flow and the integration with the NVIDIA MatchLib. This tutorial is also available as hands-on material on the ESP webpage. We choose the Softmax function as a running example for the tutorial. In machine learning, Softmax is a widely used activation function. You find it usually at the end of a deep neural network because it turns scores, floating point values, on an arbitrary range into probabilities. The sum of the output values is 1. The Softmax function outputs a vector that represents the probability distribution of a list of potential outcomes. For example, if you're running a neural network to classify animals, Softmax returns the probability for the image to be a dog or a cat. You can also see the mathematical definition of Softmax. For each value, we have the exponent of that value divided by the sum of the exponent of all of the other values. We choose to leverage an open source implementation of the Softmax, as it is provided by Mentor on hlslibs.org. This implementation uses piecewise linear approximation and algorithmic C data types, Mentor ACFix. The input and output arguments of the function are parameterized so that the arithmetic can be performed at the desired fixed point precision. This allows the HLS designer to trade off among area and performance. During this tutorial, we will not explore the capabilities of the HLS tool for the design space exploration, but we will focus on the accelerator interface, general structure, and integration in ESP. As a preliminary example, this is how you would use the Softmax function from Mentor in a generic design. I just want to highlight how the function takes as input arrays, output arrays, use ACFix as data types, and that you can choose the precision of the input and output values. For example, here we are using ACFix on words of 16 bits, 8 bits for the integer part. The first one has sign, the second one is without sign. We use truncation, and in case of overflow, we choose to saturate. You can find the material of this section on the ESP webpage. The material contains the following code: the HLS project, that is the C++ source code, the test bench and the Mentor Catapult HLS script for the Softmax accelerator, and the software, that is the application and the device driver for the Softmax accelerator. Apart from minor code edits and console commands, you are not required to explicitly code, but we invite you to review the provided code and scripts when you will try it after the tutorial. To begin with, let's make sure to be in the ESP root directory. We want to move in the accelerators and then Catapult HLS directory. Here we will download the package with the material for the tutorial. We uncompress the package and we remove the zip file. In the next slide we will see the directory structure and some more details about that. We adopt some naming convention for accelerator that we design with Catapult HLS. We use CXX_catapult suffix for the accelerator for the HLS C++ flow. We will use the _sysc_catapult suffix for the System C accelerator. The name of the accelerator for this tutorial in particular is Softmax_CXX_catapult. If you have correctly uncompressed the tutorial material, the files for the HLS project and the software application will be in the directories hardware and software. Let's see more in detail the directory structure. In particular for the Softmax CXX Catapult, we will have an hardware and software directory. In the hardware directory, we have an XML file that contains the accelerator description and the register list. As well as we have an HLS directory for the HLS scripts, some directory for the sources of both the synthesizable code and the test bench. As well, we have a software directory for the bare metal application and for the Linux application that comes with device drivers. Before giving more details about accelerators in ESP and Catapult HLS, I want to introduce a classification for accelerator for heterogeneous system on chip. We can classify accelerator according to how they couple with the processor and the memory. There are essentially two main classes of accelerators: tightly coupled accelerators and loosely coupled accelerators. Tightly coupled accelerators sit in the CPU proximity. They usually share CPU resources, such as the register file and the memory management unit, and the caches. There is no overhead for the invocation, and they are virtually transparent to the software. On the other hand, they require an expansion of the ISA to include special instructions to manage their operation. This ISA expansion percolates to the software via a compiler or via low-level libraries. These kind of accelerators, tightly coupled accelerators, pose time enclosure challenges. The logic must meet the same constraints of the CPU and may have limited portability across different designs at different CPUs. The second class of accelerator is the loosely coupled accelerator. They have a greater area budget. They cannot degrade the CPU performance. For loosely coupled accelerator, we are able to tailor the local memories, and in particular, we can move data among the accelerator, the private caches, the last level caches, and the main memory. The ESP accelerators follow this second model. These accelerators are integrated in an ESP instance as devices that we control via Linux device drivers. The ESP accelerators operate on large dataset, and they alternate computation phases with data transfer phases. Now let's consider first the interface of an ESP accelerator. The interface of an ESP accelerator has ports that are common across all of the supported HLS flows, as shown here in the figure. And in particular, there are some minor differences that are HLS tool dependent. We will see the details for Catapult HLS in the next slide. But first of all, let's see which port an accelerator, an ESP accelerator, should have. To communicate with the CPU via memory map register, we have a conf info port. These encapsulate essentially the accelerator configuration, memory map registers. Then to program the DMA controller, we have two ports, DMA read control and DMA write control. These encapsulate the DMA configuration. To transfer data from and to the main memory, we have DMA read channel and DMA write channel. Finally, there is a port to notify the task completion back to the software application, AC done. And this can be mapped either on a register or to an interrupt. Given the previous overview of the interface of an ESP accelerator, we can see here the C++ code for the module interface when we run Catapult HLS. You can see that we are using Mentor AC channels and AC sync. The AC channels is a communication channel that allows the accelerator to transfer data to and from a top module. When combined with the HLS directive CSS IOPort.css in wait, it ensures that the data is properly synchronized at the interface via latency-insensitive protocol. Catapult adds the proper handshaking signals to the RTL netlist in form of read, valid, and data signal. While the AC sync port is a synchronization channel that Catapult offers for specifying standalone handshaking signals when a designer needs to control the synchronization directly. Essentially, there is no data transfer. And it is here combined with the directive IO port sync out valid. In addition to the communication and synchronization channels, the accelerator interface relies on the following data types. We have a data type, more properly a C++ structure, for the configuration register that are memory map, conf info t. In this case, for the Softmax, there is only a single register for the size of the batch. Then we have a data type to specify the DMA configuration, and in this case, this struct has an index, that is the memory offset, as a field that is length, that is the length of a DMA transaction, and there is also a field size, that is the encoding of the DMA width. This second struct, this second configuration, is common to all of the accelerator, while the first one, the conf info, has to be customized according to the necessity of a designer. Finally, the designer can specify the size of the DMA word with the DMA width macro. This can be 8, 16, 32, etc., and that will impact the overall system. After HLS, this is how the interface looks like in RTL Verilog. You can recognize most of the ports that we have previously defined in C++. Besides the data channels that comes with the suffix _dat, you can notice the additional _ready and _valid channels that implement the latency insensitive protocols. Let's see hands-on the accelerator interface in C++, how to run HLS, and the same interface in the generated Verilog RTL. We have previously downloaded and uncompressed the tutorial material in the directory catapult _HLS, and at this path Softmax cxx catapult hardware source basic softmax.cpp, you can find one of the two implementations that we will present in this tutorial. If we open the file, we can immediately recognize the interface that we have previously defined, where we have AC channel and AC sync primitives. For the AC channel, we have the configuration channel to access memory map registers. We have the DMA read and DMA write controls channels. These are to program the DMA, and then we have the channels to move data from and to the main memory. If we want to run HLS, we have to move to a different directory. In the specific case is SOCs, and we choose a specific target board. Once there, we run the synthesis command. Keep in mind that this makefile the targets for this makefile get automatically generated when you uncompress the package. Running HLS for this accelerator may take few minutes. Once synthesis completes, we can check the generated RTL code. The RTL files will be placed in a directory that is technology and accelerator specific. Here we can find our Verilog file. It's relatively big. And closer to the bottom, we may recognize the RTL interface for the Softmax accelerator, where beside the clock reset, we can find all of the other channels that we have designed in C++, together with the extensions that suffixes. that specify that a specific channel is for data or is for synchronization with a latency insensitive protocol, because we have these valid and ready signals. Internal structure of the ESP accelerator. Let's remember that the accelerators in ESP are loosely coupled and that the accelerator execution consists of 4 phases. There is a configuration phase, and after that the accelerator iterates and possibly pipelines load, compute, and store phases. For Catapult HLS, we have defined 2 different coding styles. A first, more simple style is the single block architecture, where the phases run in a sequential way and are implemented in a single C++ function. Then we have defined a hierarchical block architecture coding style, and in this case the phases run concurrently one to the other. In particular, to add concurrency, we combine HLS directives with a recommended coding style, while still leaving everything in C++ runtime and single-threaded. The synchronization between the blocks will be added automatically during the synthesis process, and we will see these 2 coding styles in a couple of slides. Finally, let me also stress the importance of private local memories in ESP accelerators. In the PLM, the accelerator keeps a copy of the data or a portion of the data from the main memory. The PLM becomes central for the design optimization process because they can be tailored to the needs of the designer. We have usually local memories to support each of the load, compute, and store phases. Sometimes PLMs have to be implemented as circular buffers. In some other cases, they are ping-pong buffers. In most of the cases, the designer has to create PLMs with many ports to sustain the throughput of the accelerated logic. More in general, a properly tailored PLM reduces the latency and increases the throughput of the system. Let's consider the simplest style. The main characteristics of a single block architecture are: the phases run in a sequential way and are implemented in a single C++ function, and the private local memories are defined locally to the C++ function. You can see here the pseudocode for the Softmax function, and we will see the C++ implementation in a minute. This is just to give you an overview of the implementation in a single slide. On the top, we have the interface that we have previously defined, here, the signature of the function. And later on in the function, we define the local memories, the PLMs, as arrays. Then we have the configuration phase, where we read from the conf info port the memory map register. In this specific case, we read the batch size of a softmax. That is the number of times we later on iterate over load, compute, and store. During the load phase, we configure the DMA controller with the offset in main memory and the amount of data we want to load. We use the DMA read control port for this. Once the DMA is programmed, we can start reading the DMA read channel and saving data in the PLM. For the compute phase, we leverage the Mentor Softmax, and once the computation is completed, there is a store phase. Similar to the load, we configure the DMA controller, and then we start storing data back in the main memory. The actual code for the single block architecture is pretty similar to the pseudocode. The only implementative detail that I want to highlight is that it is necessary to explicitly enforce the serialization between the DMA configuration and data transfer subphases of both the load and store phases when coding them in C++ for HLS. For example, you can observe here again the single block architecture, the simplest one, and later on in the code we may observe the configuration of the DMA read channel. How this configuration is performed. We define a flag, DMA read control done, and we iterate over this DMA read control done by using a non-blocking primitive. We try to write DMA read control until we succeed. When we succeed, we have a true value for this DMA read control done. Now later on, we test that variable. Essentially, we force a serialization between the DMA control up here and later on the data transfer. If you do not use this simple trick, the final RTL code is not functionally correct. And what we observe, what happens, is that the data transfer starts before the configuration of the channel has completed. And you will notice that if you run a RTL simulation, obviously that would cause an error. Here you can see the coding style that we have adopted for the hierarchical block architecture. The main characteristics are that the phases are coded as separate C++ functions. The PLMs are globally defined and shared among the functions. Note that Catapult offers the modeling construct AC channel to allow the users to directly model the data exchanged between blocks of a hierarchy. While in software, function can exchange data via shared arrays of variables, this becomes problematic for HLS, since the synchronization of data exchanged between blocks must be inserted automatically by the synthesis tool. Because of the inherent complexity associated with this, Catapult offers the modeling construct AC channel to allow the users to directly model the data exchanged between blocks of hierarchy. Note that the user can use the AC channel to model both I/O streaming and memory interfaces. Here at the function interface we have the I/O streaming, while here, later on, we are declaring the PLM as AC channel, and those memories are passed as parameters to the load, compute and store functions. In addition to AC channel, in this coding style we use AC sync for the synchronization of the processes and blocks. The AC sync are passed as well to the various functions, and when all of the processes have completed, they synchronize via the synchronization primitive. Finally, at the end, we return the accelerator done signal. As array sizes become larger, it is typical to map them to memories during HLS because the area and power cost of mapping to register becomes prohibitive. In Catapult, the arrays that are shared between hierarchical blocks get automatically mapped in a ping-pong memory structure. This ping-pong memory structure consists of two or more memories that are written and read in such a way that the blocks can run concurrently. And this is useful and is one of the key aspects of the accelerator in ESP, being able to tailor the PLM to keep the maximum throughput of the accelerator. Finally, in addition to the above HLS directive, a coding style must be followed to ensure that extra memories are not inferred by error. First of all, you have to remember to encapsulate the shared array in a struct, and then a local struct with the package array should be declared to perform the memory operation, and this local struct is optimized away if the coding style is carefully followed. For example, in the load function, when we transfer data from the main memory to the shared input PLM, we should declare a temporary version of the PLM, a local instance. We have to iterate over this local instance and read data from the DMA channel, and only finally write the local instance back into the PLM. The same applies for the store phase, where we read the output PLM into a temporary copy and use this copy to transfer back data in memory. In both the cases, the temporary copy will be not present in the generated RTL, and there will be only one shared memory structure between the top module and the submodules. We are getting close to the end of the tutorial. The last thing to do is to create an ESP instance with the design accelerators. Once the ESP SoC generator graphical interface is open, the very first thing that I want to do is to make a little more room for my accelerators. I increase the number of columns in the NOC. At this point I move the I/O tile. I instantiate the Softmax accelerator, the basic implementation, as well as the hierarchical implementation. And I click on Generate SoC config. At this point, what remains to do is to run make vivado sim. This will take a while, but at the end of the synthesis I will have a bitstream ready to be run on my FPGA. The material that I used during this section is available online and on the ESP webpage. It comes also with the software application and the device drivers to run your ESP instance with Catapult HLS accelerators, both in simulation and on FPGA. Thank you for your attention.